Okay, so let's start here. Hello, everyone, and welcome to a new webinar from Optiwave. This is entitled of Modeling VCSEL Transmission and OptiSystem Software. It's a realistic simulation of experimental results in optical communication system. Today, we are happy to introduce our collaborator, Dr. Chen, Chen from Corning. He will talk about the experimental part. And then my colleague, Dr. Abdullah Karar, he is a senior optical scientist at Optiwave. And then my name is Ahmed Atiyah. The webinar we're going to talk about, give you some overview about Optiwave as usual. And then we introduce our product line. Then I'll pass the podium to Dr. Chen to talk about the enhanced 850 nanometer VCSEL transmission, exploiting chirp interaction with fiber dispersion. Then my colleague Abdullah, Dr. Karar, who's going to be speaking about OptiSystem capabilities for simulating VCSELs and chirp interaction. Then we finalize question and answer. Okay, so general information about Optiwave. It's established in 1994, over 30 years ago, and we are located in Ottawa, Ontario, Canada. We develop software packages to be used in designing and optimizing capabilities of component, devices, links, systems, and networks. The software can be used to optimize the design of your devices or systems and shorten the product time for your product, and improving product quality and enhancing quality and cost effectiveness through the simulation. The product line of Optiwave is three categories. One is the system level, including OptiSystem software. We are talking about OptiSystem today. And then the other software, which is an optoelectronic software. You can simulate optoelectronic circuit in the same layout, which is OptiSpice. And then the component level category, which includes the mode solver, OptiMode, and then the finite difference time domain software, which is OptiFDDT, and beam propagation method, OptiBBM, and the fiber design, which you can design any type of fibers, single mode, multi-mode, and different index profiles in it. And then the OptiGrating, which you can design fiber bright grating, long period, short period, tilted gratings, in this kind of software. And then finally is the instrumentation software, which is you can communicate with any equipment in the field, not specific to a specific vendor. You can set up the equipment and automate setups, collect data, process data, and then also you can feed it to OptiSystem software. This is just a general overview about our customer base. We have our software being used in over than 80 countries. We have over than 3 million evaluation downloads. There is a huge customer base in industry and governmental institutions, as well as university. Just is a snapshot of some of the industry, as well as universities, which is been using our software for a long time. Now I'm going to talk about the way to download our software. You can download 30 days free trial for any of these software packages. You go to our Optiwave website and then go under downloads. You click on the 30 days evaluation, and then you need to register on our forum website. Once you register, you create your account, and then you will be able to download the software on the C drive under program files. Once you download the files, you get the download in the C drive as mentioned. And then, for example, you get the directories for the different either component or the libraries, drivers, and so on. One of the important directories here, the documentation, which has like files for the release notes, for component library specifications, for some tutorials, and so on. This is very important to look at it for using the software references and so on. An important reference for our software you can find we have a YouTube channel. It's Optiwave High Definition HD. You have all our like webinars and short videos which give information about specific components or about specific operation of the software can be found there. Also, you can access the Optiwave knowledge base documentation through our website, where you can find different examples and documentation and paper reproduction for different examples. Now I'm going to talk more about OptiSystem software and mainly about the comprehensive library of components. We have over than 625 components, which are using analytical or empirical formulas we solve them to represent the functionality, different functionality of the components. These components you can find also equipment or visualizers, which you can view the signals in the optical domain or electrical domain, binary as well as in-memory. Then we have an example library which has over than 1,000 examples. These examples can be used as a basis for building your system and understanding the functionality of the components you need to use and build. The components in OptiSystem are categorized into subcategories, which is related to the functionality. So we have a library for light sources, including analytical models for CW lasers or measured, you can measure data in these lasers. There is LEDs, VCSELs. Today is mostly we're going to concentrate on VCSELs. There is models for DFB, Fabry Bureau, and there is white light sources. Modulators, there is optical modulators, electrical modulators, which can use either analytical or you can use measured information in it. Can have Mach-Zehnder modulator with single drive or dual drive or single port or dual port. So there is lots of flexibility, electro-absorption modulators as well. There is bit sequence generators with also compliance test patterns, modulation formats. We support almost all modulation formats in the field, from return to zero to advanced modulation. Optical fiber, we do have models for single mode fiber, multi-mode, multi-core, photonic crystal fiber, hollow core fiber. As you can see here, there's some plots of different structures of these multi-core fibers and photonic crystal fibers. There is filters, electrical filters, different types, optical filters also as well. And also there is filters using Fabry Bureau or fiber Bragg gratings as well. There is modulators like orthogonal frequency division multiplexer modulators, quadrature modulator, which enables you to set up your frequency at any intermediate frequency. There is electro-absorption, electro-optics circuits exploiting the integration between OptiSpice and OptiSystem allows you to build ring resonators, laser drivers, and optical interconnect and switches. There is photonic integrated circuit devices support, where we introduced recently in the version 22.1 a new components, which one is photonic integrated circuit waveguide, where you have you can use the device as an optical waveguide with some electronics control. As well, there is a component called optical S parameters, where you can have measured S parameters and load them, and then you can use them in a circuit to represent a photonic integrated circuit. There is a new examples in OptiSystem using these components for building Mach-Zehnder modulator or Mach-Zehnder interferometer, ring resonators, and so on. There is also component for signal processing. So we have digital signal processing the component, which has comprehensive models for equalization. There is also the other different equalizations for adaptive filters and so on. We are introducing a new component called digital pre-emphasis component. It's going to be released very soon, which enables you to do electronics, analog and digital pre-emphasis in the circuits. There is FIC components. We support Reed-Solomon, low density parity check. We have bit mapping, which can be used for different kind of coding. There is detectors. We have bin detectors, avalanche photo detectors, single photon detector, photon number resolving detectors. Optical amplifiers, you can build any type of amplifiers from scratch using doped material from erbium, ytterbium, or erbium, ytterbium, tholium, praseodymium, holmium. Also, you have gain blocks using these components. You can use them in any region of operation as of interest. There is semiconductor amplifiers, there is Raman amplifier models, and there is waveguide, erbium, ytterbium waveguide designs. We also allow optimization in OptiSystem, so you can do gain flattening filter optimization. Electrical filters, there is transimpedance amplifiers, which can be in the linear regime or nonlinear regime. So you have two options to operate these transimpedance amplifiers. There is limiting amplifiers, automatic gain control amplifiers. There is also passive modules, which can be couplers, multiplexers, everything you can think of it, of devices. There is multi-mode applications, fibers. There's different models for multi-mode fibers. There's mode generators. You can generate Gaussian modes, LG modes, donuts, and different mode structures. There is special visualizers to view that, and demultiplexer as well to demultiplex the different modes. And the channels, we support different fiber channels. As we said, single mode, multi-mode. There is multi-core. We have Li-Fi channels, satellite channels, free space optics, underwater optical communication, visible light communication possible. Visualizers, as I mentioned, we can cover all the fields, optical, electrical, binary, memory. There is test equipments like PERT, a light wave analyzer. And the components, most of the components can be either in the signal unidirectional or the bidirectional, so you can do transmission in both directions. OptiSystem tools, we also offer optimization tools. You can optimize single parameter or multi-parameter optimization. We have Monte Carlo optimization. We have gain flattening filters, as I mentioned. There is a new tool we added up, which is a machine learning tool. You can train the system, test the system, as well as doing predictions. So you can load, let's say, eye diagram or something, or certain images, and then you can predict the performance of the system in terms of length or any condition you train the system on it. As you can see, this is the machine learning tool added up into the OptiSystem. Then there is the example library, as I mentioned to you. There is these examples are categorized in the different categories depends on the application. There is advanced modulation, new radio front haul, optical amplifier library, microwave photonics, sensors. You can have Phi OTDR, OTDR. You have different types of sensors applications. We have allowing photonic crystal fiber for biosensing through you design your photonic crystal fiber using OptiMode, and then you import it into OptiSystem and do sensing it. There is some examples there. There is the different examples on wireless communication. There is spatial division multiplexing for few modes or multi-mode fibers or single mode or multi-mode multi-core fibers. There's examples on quantum key distribution, digital image processing. You can do the digitization of image, black and white or gray or colored images, and you can transmit them over the different channels. There is the photonic integrated circuit characterization, enabling use the new components we added up, and then the machine learning. Okay, so the last thing here I'm going to talk about before we move to the next section is the integration of OptiSystem with other software packages like OptiGrating, OptiSpice, OptiMode, OptiFDDT, and OptiInstrument. And we also integrate OptiSystem with other external software like MATLAB, Python, C++, as well as Scilab. You can call OptiSystem from this software, or you can call this software from OptiSystem. So you can have bidirectional communication with this software. And then the integration with EPCAS from Lucida to allow using photonic integrated circuit devices into OptiSystem. We did a couple of webinars with Lucida. You can find these webinars on our website or YouTube channel to learn more about the using Lucida component and how to use photonic integrated circuit system characterization. Okay, and then here I'm going to move right now to Dr. Chen from Corning. We are happy to have him here to talk about the experimental part for exploiting chirp for integration with fiber dispersion. So I'm going to move on to the presentation here, and then give the podium to Dr. Chen. Go ahead, please.
Yeah. Thanks, Ahmed. Thank you for the introduction. Today, my name is Xin Chen from Comm. I'm very glad today I'm coming to this webinar to present some of the work we have done a few years ago on the enhanced A50 single-mode VCSEL transmission with a favorable laser chirp interaction with a fiber chromatic dispersion. This work was done with several of my colleagues, and also the papers detailed information is listed here, and you can go online. It's an open access paper, so you can find all the details from the paper in addition to this presentation. Next slide, please. I work in the short reach optical fiber communication where the VCSEL vertical cavity emitting laser would work with multiple fibers to form a very cost-effective ecosystem. Right, multiple fiber has a very large core, so that it is easy for the light to be coupled in, so it's widely used. And such systems have climbed the data rate from 1G, 10G, 40G, 100G, 400G to 800G, and moving toward 1.6T. At per lane level, that IEEE has standardized 100G per lane, and certainly the newest development is working toward 200G per lane. And as data rate increases, the system level bandwidth become a limitation. So people try to find other ways to for the next generation VCSEL fiber ecosystem. So we have done our work in this context, specifically related to single-mode VCSEL, which is a very active research area. And a few years ago, when we studied single-mode VCSEL, we found out when we transmit through very high bandwidth two-mode fiber, that with the fiber, the transmission performance actually can perform even better than the back-to-back, which is very uncommon. Upon the very detailed investigation, we identified the mechanism and which are related to the transient chirp of the single-mode VCSEL, which is negative chirp, interacting with a very negative chromatic dispersion of fiber, so that they can compensate the impairment instead of showing penalty. Actually, with the fiber that we see transmission enhancement. So in our very detailed investigation, we have conducted 3 lines of experiment. The first experiment is the transmission experiment with the fiber length from 300 meter to 1.5 kilometer. And also we measure the system bandwidth to see the reason we have the transmission enhancement. And most importantly, we measure the chirp parameter to definitely confirm the mechanism. So next slide, please. So here in the first experiment, what we have done is the transmission experiment. So the single-mode VCSEL is directly a modular laser, so that we use a pattern generator to drive the VCSEL. Certainly, we would provide DC voltage as a bias. And also the fiber we utilize actually is a very novel fiber. It's a graded index single-mode fiber, but two-moded at A50. As I will show, it has a very high bandwidth of 48 gigahertz kilometer at A50. And also we show the optical spectrum of the single-mode VCSEL, which has a center wavelength of nearly A48 nanometer, so it's very close to A50 nanometer nominal value, and also it is the dominant of a single-mode VCSEL. even though you could see a second peak, they are at least 45 dB down. So it has a very narrow line width, and the narrow line width is traditionally what people have explored for the transmission benefit, so that you will have a negligible or very small chromatic dispersion related bandwidth, which is a major penalty when using the commercial available multi-mode VCSEL. And here on the bottom right, I show the LRV curve. So these are the basic information that characterize the VCSEL. Next slide, please. So here I have a slide to show you what fiber we use. Actually, the detailed study of the fiber was done in 2019 in the Optical Express paper. What we found out is outside people's typical expectation, the standard single mode fiber of particular type of gradient index type could possess very high bandwidth at A50. Not every fiber is the same. So here what we show is one fiber we have identified, and we measure the group delay difference, which we turned it as a model delay, and show its wavelength dependency. And the wavelength move from 800 to 900. It goes down and at some point cross zero. When it crosses zero, you actually reach a point of having infinite model bandwidth. So that's why this fiber has extremely high model bandwidth at A50. It turns out that this zero crossing point is at A49.7 nanometer. So that at that point you reach a very high bandwidth. But our measurement say at a 50 nanometer show at least 48.3 gigahertz at 1 kilometer level. And just note that our laser is centered at A48, so it still possesses very high model bandwidth. Next slide, please. So that in the first experiment, we have done the transmission experiment. This is also a typical experiment many researchers have done to characterize the transmission performance. And using our equipment, we have done the NRZ transmission at 25 gigabit per second. And we have measured through the fiber back to back at 300 meter, 500 meter, 1,000 and 1,500 meter. One thing that stands out very significantly is that when you actually engage the fiber, depending on the fiber length, the more fiber you put in, the more transmission benefit you would observe actually that the effects start to show even at the 300 meter. And when we reach 1,000 meter and 1,500 meter, the difference becomes slightly smaller. We believe that in this case it's because the fiber does not exactly have infinite bandwidth, so that at that very long length, slightly model dispersion penalty kicks in. But overall, we do observe that introducing the fiber into the system actually makes transmission performance better. Next slide, please. In the same experiment, we also collect eye diagram. And obviously, what we observed is with the engagement of actual fiber, the eye diagram are not degrading even with a longer and a longer length. Of course, with the longer length, the eye diagram could be slightly more noisy because you receive a little bit less power in the receiver. And also a subtle aspect you could see is that with more fiber, you actually can see a slightly sharper rising, falling, and also overshooting, which usually is a phenomenon associated with more bandwidth, or maybe more bandwidth than needed. So the eye diagram result are consistent with our transmission rate. Next slide, please. In the second experiment, we want to confirm that the system bandwidth, right? So the system bandwidth would include the VCSEL receiver and the actual fiber, and we can observe that in the S21, which is usually called transmission, that with more fiber, when you get to the 3 dB level, you actually have more bandwidth, which is very contrary to the traditional system that once you introduce fiber, the system bandwidth would drop quickly, and that set a limitation how long you can transmit. But in this case, that we captured the bandwidth threshold on the right figure, and you see that the system bandwidth actually is increasing only when it reaches 1,000 meter and above, that it flat out and drop a little bit, as I explained that because the model bandwidth effects start kicking in very long length. So this is the second experiment to very explicitly confirm that the bandwidth enhancement is associated with more bandwidth in the system. So next, we will proceed to the next slide for the third experiment. The chirp measurement has been very common when people use the with directly modulate the laser, typically in the C-band 1550, and this is the method we copied from the textbook level. So it's a classic method, and the system is very similar to what we use, except that we are not using pattern generator to drive the single-mode VCSEL, instead of using network analyzer, VNA, vector network analyzer, to provide a sweeping frequency from nearly zero frequency to 30 gigahertz, and we can see the response. And in the little chart here, highlight here, you actually see multiple dip in the transfer function, or S21, and the dipping frequency actually can be captured by the analytical equation here, so that the position of the dipping frequency F0, F1 are associated with the chromatic dispersion, the length of fiber, and also alpha parameter, which is a parameter characterizing the transit chirp. So next slide, please. So we further process the equation from the actually the first equation is directly from the book, so that it show you from using two neighboring a dipping frequency, you can get the total chromatic dispersion down into equation along with center wavelength of the laser. But when you want to retrieve the alpha parameter, that you can also use the first and second dipping frequency. And also, I want to note here, you get the alpha parameter, it also carries the psi. In our experiment, and also consistent with several textbooks, the alpha parameter retrieved is negative. We wouldn't know that in the literature, people could use a different convention and maybe inherit from a very famous paper which got the sign wrong. So if you see the same thing and tell you two signs, they are all possible. You need to follow a particular convention. So next, we show the next slide, please. We show the actual measurement result, which is the total system level S21 or transmission, and you can actually see the two dippings. In this case, we used a more than 10 kilometer of single mode fiber, single mode at 850. So this fiber is actually a specialty fiber, not transmission fiber, so it's not very common for people to have. Unlike in the C band, people can use standard single mode fiber. 850 single mode fiber is a special fiber, and we can extract the first and second dipping and use that to calculate the alpha, which is a minus 3.52, and also the chromatic dispersion of fiber is minus 1.3, which is highly consistent with our known knowledge or a calculation from alternative method. So here we confirm the single mode VCSEL has a very strong negative chirp, so which consistent and explained the experimental observation of transmission enhancement. Next slide, please. And here we showed a more recent collaboration with National Central University, which based on the single-mode VCSEL they have fabricated, and with very high bandwidth, they also confirmed they could have a bandwidth enhancement with more fibers. Actually, they are with long than the same fibers, so at 100, 200, 500, 1,000 meter, and they clearly see the bandwidth enhancement and amount you observe, which is very significant. So looks like this is a very across the board universal effect, but because we can access specialty single-mode fiber at 50, so we can use direct chirp measurement method. Finally, the conclusion. Next slide. So that we after we have observed the transmission enhancement, we attribute this to the favorable laser chirp chromatic dispersion interaction. And I would emphasize using the chirp convention, it is a negative chirp working with a highly negative chromatic dispersion to have enhancement. If you flip the side of the chirp or flip the side of chromatic dispersion, you would see a penalty, very strong penalty, more than average. And we have shown 3 different ways to verify the effect. With that, the very interesting aspect is if all these physics, single-mode VCSEL physics, and the chirp chromatic dispersion interaction can be modeled by OptiSystem software. So with that, I will pass to Abdullah for the next portion of the webinar.
Thank you very much, Dr. Chen, and then we'll move now to next speaker, Dr. Arar. So if you want to go ahead, please.
Thank you very much, Dr. Ahmed and Dr. Chen, for the introduction. I'm just going to share my slides here. So thank you, colleagues, for this introduction. So basically, the purpose of the remaining part of this webinar is to try to do 2 things. The first one is to demonstrate the effect that Dr. Chen has shown us experimentally, which is the benefit in transmission when you have a negative alpha parameter for your direct mod laser or VCSEL in this case, and a negative dispersion. So we're going to be focusing on a specific publication that Dr. Chen and his colleagues have demonstrated this effect for the 25 gigabit per second VCSEL. We'll show how to set it up in OptiSystem and go over some of the key parameters needed to verify this result. Furthermore, I'll also look at large signal dynamic modeling of VCSELs and DML in OptiSystem. And this relies on using, for example, in this particular webinar, 2 of the laser measure components, 1 VCSEL and 1 for regular DFB laser, where we measure the small signal responses in the laboratory, and then with knowledge of the subtracted IM responses, IM here refers to intensity modulated responses, these are small signal responses, and knowledge of the threshold current of the laser and the slope efficiency of the Li curve, we could obtain exceptional agreement between the measured eye diagram in the laboratory and the simulated eye diagrams in OptiSystem. So without further ado, I'll just go over the first part. So in this sense, we're attempting to reproduce the work done in the OECC paper by Dr. Chen and his colleagues. And in this paper, they demonstrated 25 gigabit per second transmission over 15 kilometer of G652.D fiber. So the fiber parameters are mentioned in the paper. So here I'm just going to highlight the parts that are relevant to this modeling in OptiSystem that we're going to be using in the modeling process. So what's mentioned is the zero dispersion wavelength, the dispersion slope of the fiber, and in the publication, there were 2 types of fiber examined. One of them is fiber 1 and another one named fiber 2. The first is 15 kilometers and the second is 10 kilometers. But they are different fibers. They have different characteristics. So for the purposes of this demonstration, we'll focus only on the 15 kilometer fiber. And as you can see here for this figure B and C, show the total dispersion for this 15 kilometer fiber and the also attenuation profile for this fiber. And the purpose is to demonstrate the interaction of the alpha parameter or the line width enhancement factor, as Dr. Chen has pointed out, and the sign of the dispersion. And as you operate this laser at a particular wavelength, and obviously you have a different laser at a higher wavelength, but if you're operating in this region, you get a benefit, and if you're operating in the other region, you get a penalty. So we're trying to show that in OptiSystem. That's the purpose of this demonstration. So what we can see here is an example of some of the published experimental measurements. And for the sake of brevity, we'll be focusing on two particular wavelengths. One of them is located far away from the zero dispersion wavelength, where the amount of dispersion is negative and the alpha parameter for the transmitter is obviously negative. And in this case, we'll end up seeing some benefit. And for the sake of clarity, we'll be only looking at a 15-kilometer fiber and focusing on the bit error rate threshold of 10 to the -9. And this is where we're going to be determining the penalty. So if you observe this operating point, you can see that at 1267.5 nanometers, there's about 2.8 dB penalty, sorry, dB improvement, my apologies, relative to back-to-back. So you can see now you have a lower received optical power. It's 2.8 dB improvement. And if you're operating at 1374.5 nanometers at the same threshold, BR threshold, you have a 3.5 dB penalty. So as Dr. Chen has pointed out, you do actually see significant improvement when you have the sign of the line with amps factor is aligned with the sign of the dispersion in the fiber. So in an effort to also demonstrate this, there were some measured eye diagrams in the publication. And since we're focusing on the 15-kilometer fiber, you can see here that the eye diagram at back-to-back and the eye diagram after transmission is more open. So this is actually indicative of this benefit from this alignment of the sign of the dispersion with the sign of the alpha parameter. Furthermore, at 1374.5 nanometers, you get a degradation and the eye is closed after transmission. So back-to-back relative to transmission. So later on in this webinar, we'll show how you could replicate some of the measured eye diagrams and what are the needed ingredients to demonstrate this in OptiSystem. So if you take from the publication itself the total dispersion versus wavelength, then you can actually, for the sake of this demonstration, we're focusing on these two wavelengths. You can certainly take the static number of the dispersion and you can set it in OptiSystem's component, although this requires you to reproduce a duplicate of the fiber and change the numbers for each wavelength. Or you could simply load in OptiSystem the measured file with all the different dispersion values for many different wavelengths, and that just enables you to change the wavelength with the same component. So this is something we'll do here as well. For the loss or the attenuation profile in dBs per kilometer, we're operating at these two wavelengths. We can read this loss profile into a file and upload it into the fiber component in OptiSystem, and allows you this flexibility to be able to run the same model at different wavelengths without changing the static parameters. So the setup is fairly straightforward. We're obviously simulating an on-off keying system. So here we have the VCSEL laser operating at the wavelength of interest that we're examining. We have the line width enhancement factor set to -3.5 in this case. And we have an optical amplifier, try to make the power launched into the fiber 2 dBm, which is what's been stated in the article. And then we have the fiber model, and this is the general layout for the parameters in the simulation. We're operating at 25 gigabit per second here, and we're using about 1 million bits for simulation modeling. So since we're operating or trying to really measure the bit error rate performance at 10 to the -9, we can't do direct error counting. It's going to require a significant number of bits. So we're going to be using the semi-analytical approach for calculating the bit error rate. So this number may be a little bit excessive. You can probably get away with something a little smaller. And the fiber, we set the reference wavelength to the transmitter wavelength we're interested in. And you can see here, this is the attenuation versus wavelength file that we load in. And there's also a dispersion file name, which is dispersion versus wavelength as well. So that allows us to change the wavelength of the transmitter independent of the fiber. And for the bit error rate analyzer, these are the setups. We can ignore a certain number of bits before and after to try to eliminate some of the transients. And we're using the chi-squared semi-analytical bit error rate measurement method, which, in my experience, provided some very adequate comparison with experimental measurements. So one critical parameter to take into consideration when looking at these models is the optimization of the biasing of the laser. So this is very critical. And for this particular wavelength, for the 1267.5 nanometers, we can set a specific received optical power where your bit error rates are not too good and not too bad. So you're in a sweet spot where you can actually measure those bit error rates and in simulation and determine the optimum bias conditions. So you can see here as we decrease the bias current, for example, 8 milliamps versus 16 versus 4, you get a sweet spot. So as your bias gets lower, the zero rail of your on-off keying signal becomes lower in power, so it carries less noise when you go through direct detection. But they're up to a point. So for example, if your bias is too low, you start getting a lot of the relaxation oscillations and the dynamics of the laser kick in, and your eye is closed at back-to-back. So that offers you a significant sign that you're not in the right position. So same thing happens for the 1374.5 nanometers. Now, these values are relative. They assume 1 ohm termination. And we're going to find a sweet spot, let's say, for this laser transmission at 4 milliamps in a peak modulation, and also for the 1374.5 nanometer wavelength. Now, combining those together and actually running the simulations, you can see that relative to the back-to-back performance, we have indeed at 10 to the negative 9 bit error rate, we can see that OptiSystem does actually predict the same physics that Dr. Chen has demonstrated experimentally, which is a benefit at 2.8 dB with 1267.5 nanometers and a penalty at 1374.5 nanometers. And this actually does indicate that the sign of the alpha parameter relative to the dispersion is actually critical. There has been other publications that show different transmitters and how dispersion and the alpha parameter come into play. And this paper by McGill University in Optics Express shows the sort of theoretical formulations for the small signal response with the different transmitters. And the small signal response is actually critical because from it you can attempt to extract what the alpha parameter is. And this is actually an important step for the modeling purposes. So here I'm going to show a way to generate a small signal response in OptiSystem, which is quite useful and may not be very trivial right away. So in an effort to do this in OptiSystem, you need obviously to measure the response of the transmitter with the fiber present. So it's a small signal response with the transmitter and the fiber, and you have a pin receiver. And we're using here the electrical filter analyzer component. So that takes in an electrical input, electrical output system and gives you a response of the system. So we're going to be doing this here with the transmitter of the fiber and the laser together. And you need a clock recovery module to align your transmitted signal with the received signal so you can calculate correctly what the frequency response is. And you can finally look at this with a dual RF port analyzer. And just by way of an example, if we set the parameters to the previous transmission simulation to 1267.5 nanometers and 1374.5, you can see that there's a slight improvement in the bandwidth of the null point when you have this negative alpha and negative dispersion. So this is certainly a contributing factor to the experimentally observed enhancement seen by Dr. Chen and his colleagues, and also demonstrates also part of this improvement in dB that we observe in OptiSystem. So what we've shown so far is OptiSystem can effectively replicate some of the physics outlined in other publications and has the ability to have a robust modeling tool. Now, we can always use OptiSystem for something more in regards to the large signal dynamics of the lasers. And this relies on getting some very good alignment between experimental measurements and the modeling done in OptiSystem. And I'll demonstrate a few examples of this. And in order for us to do this, we have to look at two components, for example. One of them is a laser measured and the VCSEL laser measured components. These components are fairly comprehensive and offer you an ability to accurately reproduce the large signal dynamics of the laser. So these components rely on a few key measurements that you do in the lab. The first one is small signal response. So you would operate your laser at two different bias conditions, and from these bias currents and Li curves, the bias IM responses, you can subtract them and get a subtracted response. You supply the subtracted response to your measured component in combination with the threshold current, the slope efficiency, some other parameters related to the line width. And you could essentially have a very good model of the large signal dynamics of the laser. So in an effort to do this, I'll just demonstrate sort of one case of running this module component, for example. So in the main tab, you can set the frequency and the bias and modulation current. And you have also inclusion of thermal effects. This is actually very important in some applications. And you could, for the measured component, this is in the measure tab, you have an ability to supply the engine OptiSystem uses for fitting the rate equation parameters with some key parameters. The first one is that you can either supply from a file the subtracted IM responses that we talked about before. And the benefit of using the subtracted responses is that it eliminates the common mode electrical parasitics. So you're getting a true measure of the laser dynamics that you can use to fit the rate equation parameters. You can also supply a threshold current and an operating point where you want the fitting engine to work. You can also supply the slope efficiency in milliwatts per milliamp of the Li curve, and some important information regarding the relative intensity noise, where it starts to ends in the bandwidth and how much RIN is there in the system. And that obviously has an influence on the line width enhancement factor that the system extracts at the end. There is a tab with physical parameters, and I want to highlight that this tab actually doesn't have the parameters used in the model. It just has the initial conditions. So these are your initial conditions that you provide to the fitting engine in combination with these measured metrics. And then the fitting process starts and you get the real rate equation parameters that run in the simulation. Now, how do you find those final results are actually in the results section of the component. You can always enable graphs as well to see what the Li curves looks like, to see if you can get a good agreement. So you also note that this fitting works with the rate equation parameters, 9 specific rate equation parameters, and the line width enhancement factor is primarily affected by the line width measures that you put in here as well, and of course your starting condition. So if you roughly know what your laser line width enhancement factor is, you can set it in, and then you can look at your measured line width and you can get an optimum number that you can use in your simulations. So from my experience, there are essentially 4 key ingredients that you could rely on that could be very beneficial for modeling lasers. The first one is extraction of the small signal responses measured to different bias conditions, and you can supply those to your laser measured component or your VCSEL laser measured component. The second one is getting the alpha parameter, and you can actually measure it in the lab using time-resolved chirp measurement techniques, or you could use the method that Dr. Chen has pointed out, where you with fiber dispersion and knowledge of the fiber dispersion, you're able to, with knowledge of the fiber dispersion, you're able to determine the null points and extract the alpha parameter. And furthermore, if you successfully obtain the rate equation parameters, you could essentially model the laser parasitics. So you can get a model of the laser parasitics and extract it. And finally, the optimum bias conditions of the laser are essential. So let's take an example of this laser here used in this publication, and it's a PsyOptics laser. This is a legacy system. Nonetheless, it's a very good way to demonstrate the capabilities of OptiSystem. And here we're measuring the intensity modulation response at 2 different bias conditions, about 1.18 I threshold and 2.6 the threshold current. And if you subtract IM responses, you can take this subtracted response, load it into a file, and provide it into the laser measure component. And the measure component produced for you the various rate equation parameters here. And with the exception of the line width enhancement factor that you can set with a good guess or with some of the measurements of the line width. These are examples, some of the traces from OptiSystem simulation of the Li curve after fitting, and also the small signal dynamics at 2.5 gigabit per second with measured and rate equation model from OptiSystem. So this is the intensity. For the phase, you can use advanced test measurement tool to measure the line width enhancement factor and get the adiabatic chirp and transient chirp as well. Or you could rely on the method Dr. Chen pointed out, where you can actually get the alpha from knowing what the fiber transmission distance is and measuring the dips in the fiber transmission, the power fading dips, that is. Now, with knowledge of the rate equation parameters in this small signal response and knowing the measured response, you can actually subtract them and get the parasitic. So this is the electrical response of the filter that is affecting the bond wires into the die of the laser. Now, in OptiSystem, you can actually take this measured frequency response and load it into a measured filter component, electrical measured filter component. And you could essentially filter your drive signal to the laser, and that would give you even a more accurate modeling of the laser dynamics. And just to demonstrate some of the sort of alignment between OptiSystem and measurements, if we examine, let's say, this case where I have a direct mod laser, an amplifier, and some digital signal processing. So here I have a simple lookup table that takes in a stream of bits and determines what the DAC sampling rates should be. So if the laser was ideal, then this lookup table will just be a binary lookup table. If you have a 0 rail, you get a 0 number, and if you have 1, you get a 1. But if you have, let's say, 2 samples per bit, you can start manipulating the drive current to the laser to suppress, let's say, the relaxation oscillations. And just to show the powerful abilities of OptiSystem, since you now align the laser extractions and also the parasitics, you could have very good agreement between OptiSystem and measurements. So you can see here on the left-hand side, we have the OptiSystem simulations of the drive of the PAM4 signal without any pre-distortion, and with pre-distortion where these peaks have been reduced for PAM4 and ORFO for binary modulation as well. And in the lab, we also have very similar performance as well, and very similar eye diagrams, where you can see a suppression using the drive signal. If we move on to something more complicated, where we now have optical fiber dispersion involved, and we attempt to compensate for the fiber dispersion, and with typical IQ modulators, you can reverse the fiber dispersion easily, since you have control of the real and imaginary of the electrical field. But with a direct mod laser, it's a single drive, so you have only one knob to change. And as you can see here on the left-hand side is a pre-compensation in simulation and experiment. This is OptiSystem, this is measurement. And the top row, this is the eye diagram at back-to-back. Now, typically you would want the eye back-to-back to be very open, but when we try to do dispersion pre-compensation, your back-to-back eye diagram is distorted. But after transmission, you have an open eye. And as you can see here, this is the simulated eye in OptiSystem and also the measured eye. And there's a very good agreement. As you can see, even the shape of the eye inside and how all the veins of the eye diagram look like. It's quite impressive. The second thing happens also for a distance of 252 kilometers, where the pre-distortion is much more aggressive. And OptiSystem produces a back-to-back eye diagram that's very closed and certainly produces you an eye opening after transmission. Finally, I'll look into one further example where we have a chirp managed laser. So the chirp managed laser has an optical filter located at the output of the direct mod laser. And this optical filter enables the FM modulation that's intrinsic with the AM modulation of the laser to hit the slope of the filter and convert into an additional AM enhancement, enhancing the extinction ratio, and also offering sort of a phase shift between the two adjacent bits and allowing you very high levels of dispersion tolerance. This was a flagship product by Finisar. And as you can see here, this is the OptiSystem modeling of this chirp managed laser without any pre-compensations. This is just pure drive, binary drive. And you can see here, this is OptiSystem and this is measurement. And these are the eye diagrams for obviously back-to-back transmission. And then after 220 kilometers, you can see that the eye is still open even after 200-kilometer transmission at 10 gigabit per second. Now, if you further propagate the signal into, let's say, 300 and up to 600 kilometers, the eye diagram and simulation and OptiSystem are very similar, but the eye is very closed. And you can't really extend this chirp managed laser with direct modulation. Now, the benefit of OptiSystem is that it allows you an ability to test things in simulation without actually going through the resources of implementing in the laboratory. So for example, in this particular example, we could simulate pre-compensation in a DSP effect in modeling. And then once it's confirmed, we can attempt to reproduce it in the lab. And historical record of having good agreement allows you this flexibility. So you can see here, the final result I'm going to show is simulated eye diagram for 300-kilometer transmission extending beyond the 200. And this is the back-to-back eye diagram at the output of the chirp managed laser. This is in OptiSystem and this is in measurement. And you can see after a 300-kilometer transmission, the eye is fairly open, indicating the successful precomposition of dispersion. And also the alignment between OptiSystem and measurement is very good. This is an example of 380-kilometer transmission. The eye diagrams are completely closed at back-to-back. And after transmission, you get an eye opening. And this is also confirming the ability to align the measurement and the simulations in OptiSystem. Thank you for your time, and I will hand over to my colleague, Dr. Ahmed. Thank you.
Thanks, Dr. Abdullah, and thanks again, Chen. So we go to basically the question and answer session. So let me go here and okay, so this is the last slide I'm going to show you. It's about the machine learning tool, how it's set up basically, and the tool. We have a webinar we actually recorded about a month ago or so when we released version 22.1. We explained all the procedure to create the machine learning tool and how to do the prediction and all of that. So with this, I'm going to basically conclude. And let me move here to a section of question and answer. And we go to the few questions here to run. So the first one is saying, can you demo how to use machine learning with eye diagram? So as I mentioned, like we have a webinar on our website as well as on the YouTube channel, Optiwave High Definition. You can see there. And if you need more information, just send us an email. This is my email address. Actually, you can see it in the slides, and you can send an email to support. Another question here is, okay. So here, can you model special or transverse modes in VCSELs in addition to longitudinal modes? So maybe Dr. Abdullah, if you can answer it, please.
Yeah, sure. So in OptiSystem, the VCSEL component itself has an ability to do spatial modes as well. And we also have mode generators as well. So it can take a signal and you can determine the mode type and the mode shape. So we have these two abilities in OptiSystem for sure.
Okay, thanks. There's a question here from Akram. If you could post your question, please, on the chat or in the question and answer window, because there's no interactive session here right now with attendees. So if you could write the question in the chat or in the Q and answer window would be great. So go another question here. Okay, so this is the question. What are the drawbacks of using SMF single mode VCSELs with graded index fiber? What are the drawbacks of using? Is there any drawbacks, Dr. Chen, on?
This is what I have reported is a research effort to explore the potentially different options. So those are based on the experimental a study, and certainly not offer as a product, but certainly using two-mode standard single-mode fiber as two-mode fiber. When the fiber is right, it has very high bandwidth, but the drawback is you need to couple the light into a smaller core fiber, so that coupling is more difficult. So that's probably the drawback in this particular setup.
Thank you. So please, if you have any question, just write it in the question and answer window or the chat, because there is no interaction with attendees here in this webinar. Okay, there is another question here. Is it possible to include inverse design in some parts of your subsystem or devices? Inverse design. I think, Abdullah, if you could please answer it.
So in OptiSystem, there is an ability to optimize some parameters. If you have a simulation environment, and let's say you want to target a bit error rates, you can certainly optimize or do multi-parameter optimization. We have also an ability to use Python scripting for a lot of the components. And this ability allows you to do, say, genetic algorithm, global optimization algorithms, or even apply your own neural networks to try to do inverse design of complex optical communication systems. So that ability is there.
So it's typically with this Python, you can do Python scripting. Your project, you can script it in Python. You can actually convert it in one of the tools in OptiSystem. You can script the whole project. And you can work actually, as I mentioned, from Python directly into OptiSystem. So you can write your codes and call components in OptiSystem from Python and connect them. And then eventually you can create the project and then run it in OptiSystem as well. Okay, there is another question here. Can I simulate coherent passive optical networks and simulate this distributed fiber sensing based on DWDM system? Dr. Abdallah, if you want to answer it, or I can answer it.
Sure, Ahmed, you answered this.
Okay, so in OptiSystem, yeah, we support the passive optical networks as well as you can do coherent communication in these networks. So should be able to do that. There is a few examples in example library about passive optical networks, and you should be able to build on them as desired. If you need any help, please just send us an email to my email, ahmed.atiyah@optiwave.com or support@optiwave.com. We could help. Another question, is there any webinar you will offer for image signal processing? Actually, we did, there is a recording for, I think it's webinar version either 22.0. There is a webinar on it where we introduced the digital image processing there. You can try to watch it on the YouTube channel on Optiwave website. You can access it. Should be, and if you have any information, let us know so we can help as well. Can fog is simulated using OptiSystem, OptiBBM fog. So if you mean by fog is the autocorrelation function, the correlation function, I guess. Can you put more information what you mean by fog, or is it a weather condition? I'm not sure, because there is some frog actually the system for autocorrelation. If you could explain more about it, would be good. If I use a multi-mode fiber with a direct single mode VCSEL, what will be the penalty? Dr. Chen.
People have studied it widely, and using single mode VCSEL, you could launch the light into multi-mode fiber differently, but the VCSEL multi-mode transmission is regulated by the standard. So if you launch from the center, a small spot, you could enjoy the fundamental mode transmission, which can have a lot of benefit. But of course, depends on the individual fiber. If you launch with offset, the result could vary and not regulated by the standard. We actually have quite a few papers studying this area. You can search our publication to get a more detailed perspective depending on how you launch the light into the fiber. So it's highly launch condition dependent.
Thank you, Dr. Chen. The fog, it means fiber optic gyroscope. So yeah, an OptiSystem actually and OptiSpice, we do have examples built for gyroscopes. So if you wanted, you could please send us an email and then we can help you on that perspective. So there is, you can design gyroscopes in OptiSystem using loops, and it's possible to do zigzag loops and control the phase and investigate the phase information of the loop. Okay, so another question here. Let me see. Are there limitations on the VCSEL's wavelength to benefit from chirp control? Like, is it like the VCSEL wavelength? Is it has to be in the 980, or it can be in the C band or L band or any wavelength?
The chirp effect we have reported is at 850, but other people have reported having the chirp at 1060. So this effect, I think, is having a chirp is more directly related to the directly modular laser in general. But the reporting the result at 850 was very new. We believe our paper was the first, but of course this has been followed by others, and also we have very recent paper in this area, so you can find out. But the directly modular laser typically has a transient chirp. This is well known. and we show that at the VCSEL region.
Okay, thank you. Okay. Our university have OptiSystem version 16 license. What measure we have to take to update OptiSystem version 21? Okay, so the current version actually of OptiSystem is right now 22.1. So there is like almost every version, there is between 5 to 10 new components or visualizers, plus the bug fixes for a few things we add up, some features in these releases. So I think if you want to upgrade, it's better to upgrade to the latest version, 22.1. If you send me an email at, again, ahmed.atiyah@optiwave.com or support@optiwave.com, we could help you with the terms and how you can upgrade. Okay. Does noise contribution analysis in fog use OptiSystem or OptiBBM? Is not OptiBBM, is actually OptiSpice. So we could include lots of noises sources in the simulation. So you can add up different type of noises. There is thermal noise, shot noise, and other type of white noises could be added up in the simulation. Again, if you're interested, just send us an email and we can try to help you there. So we are almost 5 minutes above the time. I'm gonna conclude here. I would first thank our speaker, Dr. Chen here, and also Dr. Abdullah Karar, as well as all the attendees. We will post the recording on our website as well as on YouTube channel and send also the links to all registered of this webinar. Thank you very much again and have a good day. Bye-bye.
Bye-bye. Take care.